Okay, so welcome to the last lecture on Introduction to Holography and TTbar. So it's pretty clear that it's been way more Introduction to Holography than TTbar, but so the plan is that I'll finish what I wanted to say about holography hopefully by the first half of the lecture, and then in the last half we're going to apply everything that we learned to TTbar. Sketch, of course, because we won't have the time to do it properly, but at least I hope you'll understand the idea. Okay, so let me remind you what we talked about last time. Well, so last time we, well, first of all, we discussed a little bit conformal field theories. So those are quantum field theories that are invariant under conformal transformations. We discussed the conformal algebra. It was the same as the conformal group was the same as the isometries of empty ADS in one higher dimensions. We discussed the properties of operators, what are primary operators, what are the correlation functions, and so on. And then we did some very basic ADS CFT dictionary. So we mostly discussed a massive scalar field. And the idea was that if I write it in Poincare coordinates, z and x mu are boundary coordinates, the expansion of the field near the boundary, z goes to 0, takes the form something like phi naught d minus delta, so phi naught times z to the d minus delta plus subleading, all in integer jumps from this power, plus phi delta z to the delta plus subleading, and where delta was related to the mass of the field, usually as b over 2 plus square root of d squared over 4 plus m squared l squared, and sometimes it was related to the minus. So we discussed the fact, so normally this is the non-normalizable mode, and we discussed the fact that the coefficient corresponds to the source for the dual operator in the CFT, whereas this is the normalizable mode in general, and its value represents the expectation value of the corresponding CFT operator of dimension delta, which is related usually to the mass of the bulk field via this relation. Okay, so that's the expectation value. So that's the standard quantization. However, we briefly also discussed the alternative quantization, which is possible when this square root is in between 0 and 1. In that case, you could be choosing to fix this guy and let this guy fluctuate. That's also possible. So that's called alternate quantization. In that case, the dual theory will contain an operator whose dimension is related to the mass of the bulk field via the relation with the minus over here. And this is necessary in order to be able to have operators in a CFT that go all the way down to the unitarity bound of the CFT. So you see that picking different boundary conditions for the bulk fields results in different spectra of operators for the dual CFT. And finally, we discussed what happens if we add multi-trace operator to the CFT action. So we explained the notion of single trace, double trace, and so on. So obviously, so if we decide to deform the CFT action by multi-trace, then we found that what this does in the bulk is to impose a mixed boundary condition for the bulk field of the form phi naught minus whatever the multitrace function was. So we call the multitrace function f prime over delta fixed. So for double trace, you're going to fix a linear combination of the original source and valve. So adding this, deforming the CFT action by multi-trace is basically imposing a boundary condition where both of these coefficients can fluctuate. However, this particular linear combination is fixed. Okay, so this is what we did last time. Are there any questions about the material? Okay, so there were no questions last time, no questions now, so everything is very clear. So what we're going to do this time, I'm going to continue a little bit with holography because I want to tell you about the matching of symmetries of the theory in between the bulk and the boundary. Then I'm going to talk about how do you explain microscopically the entropy of the BTZ black hole. Remember this Becherstein-Hawking entropy with which we started in lecture 1, and then do okay. So if that's clear, let me talk about this last subject in holography, which are asymptotic symmetries. Okay, so as I emphasized in these notes, in general, the symmetries of the vacuum state, which is what we discussed in, I guess, the second lecture, are not the same as the symmetries of the theory. So what happens for CFTs is that for CFT-D, for D greater than CFT-D with D greater than 2, actually the two are the same. The symmetries of the theory are actually somebody can tell me what the symmetries of a CFT-D are for D greater than 2? Just to check you're following.
So translations, dilatations, Lorentz symmetry, and special conformal.
Very good. And what group do they form?
The conformal group, I guess.
Which is SO?
SO D, 2.
Very good. So SO D, 2. Just checking because I'm alone here, so it's very hard to, you know. Okay, thank you very much. So these are SO D, 2. And these are both the symmetries of the theory and the symmetries of the vacuum state. Okay? However, in two-dimensional CFTs, we saw that the situation was a little bit more interesting in the sense that the symmetries of the theory were this Virasoro times in D equal to 2. We had the symmetries of the theory were Virasoro times Virasoro. So these are infinite dimensional algebras. Whereas the symmetries of the vacuum were just SO 2,2. Okay, and that's because of this conformal anomaly. They didn't allow all the generators of the Virasoro, which we called LM and LM bar, to annihilate the vacuum state. Okay, so now we're interested in understanding the symmetries of the theory from a gravitational perspective, and in the case of D equal 2, we'd like to reproduce this. Okay, so as it turns out, whenever you have a gauge theory, so it can be just gauge theory or gravity, so a local symmetry, the symmetries of the theory are the so-called asymptotic symmetries. And the reason for this is that it's a general result. So you know, probably from I don't know when you do this. So whenever you have a continuous symmetry in say a field theory, there's usually a neutral current that's associated with it, and this neutral current is conserved on shell. So there's a general construction, general procedure for how to construct the neutral current in an arbitrary theory. Yeah, so in an arbitrary system, so you have some symmetry, you have this neutral current, and then which is conserved on shell, so d mu j mu equal to 0 on shell. And then how do you construct the conserved charges? Q. Can anybody tell me?
Integral of J0.
Very good. So you basically integrate, right, so d minus 1 x, normal to the time-like surface, and mu j, okay? Which is basically J0. It's exactly what you said. So you pick some spatial slice, sigma, and you integrate the normal component of the current to this slice. Now, it so happens that whenever you have a symmetry whose parameter is local, so you have an epsilon of x, or you have a diffeomorphism, which is xi mu of x, the associated neutral current, which you can still construct, on shell, it's a total divergence. So for gauge symmetries, this J mu takes the form of something that's called the on-shell vanishing neutral current. It's basically something that's proportional to the equation of motion, plus a total derivative term, which I'm going to write as d mu k mu. Okay, where k mu nu is antisymmetric in its indices. Okay, so I mean, in principle, one can prove this in 10 minutes, but I don't have 10 minutes because I have to cover a lot of material. But this is true, both in gauge theory and in gravity, that the neutral current associated to the gauge symmetry, to the local symmetry, takes this form. And what this basically means is that when you write this integral, so this J is basically a total divergence, and you can rewrite it. So initially, it was an integral of the entire surface, spatial surface sigma. Now you can rewrite it as an integral over just the boundary of sigma of d minus 2x. Okay, whatever. You have some induced matrix, whatever. But okay, so if my n mu was pointing like this, and then I have some normal to the boundary, sigma mu, whatever. Okay, so sigma, let me write sigma is here. I can also call the boundary B, maybe I'll need it later. But basically, I'm going to pick up something like, I'm not being careful about signs, n mu sigma nu k mu. Okay? So this equation is basically telling you that J0 is a total divergence, and then you use whatever that theorem is called to turn the integral over the divergence to an integral over the object over the boundary of the surface. Okay? So this is a general result, and basically what it's telling you is the following. Okay, sorry. So what does this mean? So basically, if we're saying I don't know in flat space, that is telling you that if you want to compute the charge associated to electromagnetism, you can be doing it as a three-dimensional integral if you please, but you can always rewrite that integral as an integral over a two-dimensional sphere at infinity or whatever you want. Okay? And this is something that you should be familiar from basic electromagnetism. You can compute the charge enclosed in some sphere by just computing the integral of the normal electric field on the boundary of the sphere, okay? On the boundary of the ball, let's say, okay? So all clear so far?
Yep.
Yeah. So what I'm saying is that this is the formula that you're used to from electromagnetism. Okay, but this has some consequences. So this KMU current that appears here does depend on the gauge parameter epsilon of x. And so basically I'm putting this surface delta sigma. So this is the boundary of sigma. You should think of it as lying at infinity. And what this is telling you, because the charge can be written as just an integral at infinity of this object, it's telling you that if epsilon of x just has compact support somewhere inside, if epsilon of x actually vanishes on the boundary of sigma, then the charge is going to be identically zero. Okay? So if epsilon of x on delta sigma is zero, we call that transformation a trivial gauge transformation. Because it can never contribute to the conserved charges, to physical, observables in the system. Similarly, if epsilon of x on d sigma is different from zero, then we call that a large gauge transformation. More precisely, it has to not vanish. What we mean by it not vanishing, maybe this is a bit heuristic. What we mean by it not vanishing is that it can non-trivially contribute to the charges. Okay? So Q, its contribution to the conserved charges is non-zero. So basically what this little argument is showing you that in a gauge theory over gravity, the true symmetries of your theory, so only transformations that are associated to these large gauge transformations, which can contribute non-trivially to the observables of your theory, such as the conserved charges, are physical. All the rest, all these compactly supported or vanishing on the boundary gauge transformations actually do not carry any physical informations. They are trivial gauge transformation, they're unphysical, they're redundancies of description. Okay? Is this clear?
Sorry, one thing. What is what are you calling epsilon of x?
Epsilon of x. So it's I mean, in electromagnetism, right? What's the gauge transformation? A mu goes to a mu plus d mu epsilon of x, right? Is the parameter of the gauge transformation. Is the parameter of the transformation.
Oh, okay.
Okay, in gravity, okay, you tell me, g mu nu goes to what? Infinitesimally. Plus d mu xi nu of x plus d nu xi mu of x, correct? Yeah. That's the gauge transformation in gravity, okay? But you see, in each case, it's important, these parameters, these are local parameters. So these are the global transformations are those whose parameter is a constant, whereas what we call local symmetry transformations, I don't know how they're introduced nowadays in courses, but when I was taking, introductory courses like a million years ago, people like to say, oh, we have this global symmetry, like some charge rotation, but now we want to make it local, and then, the Lagrange is no longer invariant. We have to introduce the gauge field. I don't know if you guys still do things that way, but this is what we call local symmetric transformation, and both gauge transformations and diffeomorphisms are of that kind.
Yeah, that's pretty popular. That is pretty popular still. So yeah, that's the
way. just in case, Okay, very good. So that's what I call local, and you can apply the Noether procedure to this local transformation as much as you apply it to global transformations. It's just that you're going to find this general result that the Noether current vanishes on shell up to this up to some boundary term that you can actually compute there's a procedure, systematic procedure for computing it. It's not that you're going to get some ambiguous thing. Okay, good. So, so as a consequence of this, we find that the only physical, so it's not true. Sometimes people say, oh, gauge transformations like this, you know, they're just redundancies of description and there's no physics associated to them. That's mostly true, but not fully true, because actually large gauge transformations do act as physical symmetries of your system, if your system happens to be in some sort of box that has a boundary. If your system doesn't have a boundary, then then you can forget about it. Okay, so it's important to have a boundary. Okay, good. So so we say that symmetries in gauge theories, including gravity, are asymptotic symmetries, and okay, and just some terminology. So any theory is defined, well, let's say we have some sort of concrete theory. So it's going to be defined by some action. So theory is going to be some action. But also there's going to be some boundary conditions, which I'm going to call C. So these are part of the definition of the theory. As I was telling you in the case of ADS, you know, you put different boundary conditions on the scalar field, you get a different spectrum. So it's clear that boundary conditions are part of the definition of the theory. So given the theory, say gauge theory plus its boundary conditions, you're going to talk about allowed gauge transformations, which are those such that the variation under the symmetry transformation of the fields in your theory, which I'm going to generically denote as phi. So phi is going to mean for me the electromagnetic field or the metric or whatever I may have in my theory. You want that to belong to the boundary conditions if phi belong to the boundary conditions. So that's an allowed gauge transformation. You know, if your gauge field is supposed to fall off like, I don't know, 1 over r asymptotically, you're not going to allow for gauge parameters that blow up as r to the 15, because that's going to destroy the boundary condition. So this is allowed, and then trivial. Well, trivial, I defined it over here. They're the guys who fall off so fast that they never contribute to any sort of physical observable. So then one talks about the asymptotic symmetries. Asymptotic symmetries are basically the quotient of allowed gauge transformations to trivial gauge transformations. And basically it's these ones that are the physical symmetries, the true physical symmetries of it. Okay? All clear so far?
Yep.
Okay, very good. So now just let me give an example. So let me give the example of Maxwell in ADS. So example 1, Maxwell. So the Lagrangian is f mu nu, right? Maxwell in ADS, g plus 1. So I'm going to work in Poincare coordinates, which are z and x mu. X mu are parallel to the boundary. And as I was saying, I need to have some boundary conditions. My theory is defined with some boundary conditions, and I'm going to take them to be Dirichlet. I'm saying that, so let me call this xm. Am goes to 0 as z goes to 0. Okay, I can be working in a gauge az equal to 0, which is a standard gauge. Okay, so if I work in that gauge, I'm just looking at the boundary conditions a mu equal to 0, at z equal to 0, and the question is, what is the asymptotic form of the allowed gauge transformations? Okay, so to answer that question, well, I have to do this, right? I have to, when I perform this gauge transformation, I should require that d mu epsilon, which is a function of all the ADS coordinates, equal to 0 as z goes to 0. That's my restriction on the allowed gauge transformation, which implies that epsilon of x mu and z has to go to a constant, epsilon. So at order z to the 0, it has to be a constant because then I don't have this. Of course, mu is not some. So epsilon has to be a constant, has to be completely x independent. So that's the term that goes like z to the 0, and then it has to go like z to some power. I think it should be 2, but okay, you can even think of it being linear times some, epsilon 1 of x plus blah, blah, blah. Okay, this is some positive power. Okay, then you go and compute conserved charges with this associated to these allowed gauge parameters. And what you find that for the general configurations of Maxwell fields that satisfy these boundary conditions at infinity, you find that that only this guy contributes to it has a non-zero conserved charge. Okay, basically the conserved charge is going to be the integral of the normal electric field into this epsilon of x and z at infinity. That's what it's going to be. This guy, so it's non-trivial, contributes non-trivial to the charges, but this guy is trivial. And so are all the other guys that go with even higher powers of z. So what's the conclusion? The conclusion is that, for Maxwell theory on ADS, with the Dirichlet boundary conditions on the gauge field at infinity, the true symmetries of the theory, which are given by the allowed gauge transformations modded out by the trivial gauge transformations, are going to be parameterized by this epsilon 0, which is what type of symmetry? It's a symmetry that has a constant parameter. As such, it's a global symmetry that acts on the boundary of ADS.
Can you repeat the question?
Sorry?
Can you repeat the question? What was the question?
Sorry, there was a question which I didn't hear. Sorry, am I supposed to repeat something, or is somebody else supposed to repeat something?
No, I was asking what the question was.
There was no question. I guess I was asking whether this is clear. Maybe that was the question. So how you end up? Yeah.
So in which case, for example, as a second example, in which case you will have a proper gauge transformation such that epsilon goes to 0, like for what example you will have a proper gauge transformation? Maybe it is a stupid question, but like a counterexample of this.
Sorry, what do you mean?
So I don't know how to explain it. So maybe this is a stupid question, but my question is, in what case you will have a proper gauge transformation? Namely, for what example in Maxwell in ADS, you will have that epsilon goes directly to 0, so it will not contribute to the conserved charge.
Oh, you're asking whether I can hook up? Yeah, so the general story is that I have a gauge symmetry in the bulk that corresponds to a global symmetry in the boundary. And if I understand correctly, what you're asking is if it's possible such that I just don't have any symmetry on the boundary. Is this what you're asking?
Yes, my question is that for what,
I guess
boundary condition you will have a proper gauge transformation.
Boundary conditions that are so restrictive that you simply don't find any sort of interesting conserved values. I guess that's possible. It's not very interesting, but it's possible.
No. I understand. Okay, I understand. Thank you very much. Yes.
Yeah. However, you see, it's a little bit difficult because I've just imposed a mu equal. Yeah. Okay. So I guess what's going to happen? Very good, because the charge. Yeah. So what I was going to say. Well, the boundary condition a mu equal to 0 up to some order in Z will always have a solution epsilon equal to constant, right? That satisfies a mu equal to 0 to some arbitrary order in Z. But it's important in order for the charge, so my criterion for calling a symmetry physical is that the charge be non-zero. And the charge involves both epsilon, the symmetry parameter, and the field configuration. So if my boundary conditions are so restrictive that the field configuration cannot be interesting enough, by which I mean that it doesn't fall off slowly enough at infinity, it's required to fall off too fast at infinity, then the charge will be 0 because of the allowed field configurations. And that would be a realization of what you're asking.
Okay, thanks.
Okay, I should say that also, okay, this is a bit of a, yeah, so this example is nice because, yeah, so as I probably just mentioned very much in passing, but maybe you heard it before. So you have the holographic map is between gauge field in ADS, so this AM, to global conserved current J mu in CFT. And you could have asked, how does this work at the level of symmetries? This guy has, you know, a D+1 dimensional gauge symmetry, whereas this guy has D-dimensional global symmetry. It's a conserved current. And the way that it works is that actually the true symmetries, you see that the symmetries are the same on both sides. Here is just a global symmetry in D dimensions. And here, the only true symmetries are the asymptotic symmetries of the gauge theory on ADS with these, say, Dirichlet boundary conditions. And we see that those are exactly global symmetries in one-dimensionless. So actually, the true symmetries of the theory are the same on both sides. Okay, so this is a check of the duality. Let me just say, okay, we're going to see, actually in the second example, we're going to see something a little bit more interesting where you know, the asymptotic symmetries can actually be functions of the boundary coordinates, which is way more interesting. But I should say sort of infinitely dimensionally extended asymptotic symmetries are not that uncommon. You can find them, for example, in asymptotically flat spaces in particular at non-infinity and so on. So it's you know, it's a bubbling area of research. Okay, so was this clear?
Yeah.
Yes, yes.
Okay, so let's go on to the second example, which are precisely these asymptotic symmetries of ADS3. Example 2, asymptotic symmetries of ADS3 gravity. Okay, so we previously discussed the vacuum, that's some particular state in the theory. We now want to look at, you know, arbitrary states that are allowed, so arbitrary configurations, which means that we want to look at asymptotically ADS3 spacetimes. So they only need to approach the ADS3 metric, and by ADS3 I just mean something that has, you know, R mu equals -2 over LADS squared G mu nu. This is only satisfied asymptotic. And in the middle they can do whatever they want. According to, you know, you can have matter fields, you can have other stuff. Okay, so as it turns out, asymptotically ADS spacetimes allow for a so-called Fecha-Graham expansion. So the most general asymptotic such spacetime. So I'll only do it for 3 dimensions, but there exist similar expressions in higher dimensions. So first, I'm going to go to some radial gauge. Okay, and I'm assuming that the Z mu components of the metric are 0. And then this expansion takes the form G0 mu nu over Z squared plus G2 mu nu plus dot 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 dx nu. So mu nu are boundary coordinates. This is what it looks like. So as I said, the definition is that it satisfies this Einstein equation asymptotically. And what I'm writing here is that these two things. So these are called Fecha-Graham coefficients. So first notice that this is very similar to the scalar field expansion that we wrote previously. So we're just solving the equations of motion. In the case of the metric, which has a particular dimension, these are the powers that you get. This, contrary to the scalar field, where we're just solving the linearized equation, just a linear equation of motion on top of a background, this expansion is nonlinear. Okay, so you shouldn't think of this G0 as small. And these two terms are universal, as long as the matter fields are sort of behaving well near infinity. But these terms are usually non-universal. They may depend on matter fields and so on. So these are not universal. However, if you decide to do pure 3D gravity, which is a very well-studied theory, it doesn't have any propagating degrees of freedom, but it has some nice black hole solutions, and so on. Then the expansion terminates, and there is a single more term over here, which takes the form z squared over 4, g2 mu rho g0 sigma g2 sigma. Okay, this is in pure gravity, which is a very special case. Most of our, the examples of ADS-CFT that we can believe from string theory and so on, they have tons of matter fields and other stuff. So, but people like pure gravity because it's in 3 dimensions. It seems to be, it may be UV complete, and people look for a holographic dual. Okay, now as it turns out, so it turns out that in the parlance of last lecture, this is sort of the source mode, and this is the expectation value mode for the dual operator. And what's the dual operator to the metric?
The stress energy tensor.
Very good. It's the stress energy tensor. Okay, very good. So what people normally do, what a normal person does, one wants to impose Dirichlet boundary conditions on the metric, which means that you're fixing this G0. Okay? Later in TTbar, we're going to be doing something else, but most normal people do this. Actually, most strictly speaking, you're fixing the conformal class, but let's not go into that. And then, you can again compute the on-shell action. Actually, I'm going to sketch that in a minute. You can compute again the on-shell action, renormalize it, and so on, and then you find this G2 is precisely related to the stress tensor expectation value. It's actually the stress tensor expectation value minus G mu nu times the trace. Something. Okay, very good. Now we want to look at. Okay, so this is for generally fixing G0. Now let's actually take G0 to equal the Minkowski metric on the boundary. So something that I didn't say, in the case of the scalar field, when we're looking at the phi 0 mode and the phi delta mode, they are completely unrelated by the boundary analysis. They are only related if we, went all the way in the middle of the bulk and we put smoothness or something. In the case of gravity or gauge fields, this is a little bit more subtle. There are actually a few relations that G2 must satisfy that depend on G0, and those are the so-called holographic word identities. So they follow from a near boundary analysis, which basically impose the conservation and tracelessness of the boundary stress test. Okay, so it's a bit more complicated. Again, the best references to look at are this. That is very methodically. Okay, so we take this metric to be eta mu nu. So then our metric is going to look like L squared dz squared over z squared plus, d sigma squared minus dt squared over z squared. That's our boundary metric. Actually, as previously, I'm going to want to work in terms of null coordinates, x plus and x minus, which are sigma plus minus t. And then these G2 terms, so as I said, G2 satisfies some constraints. It turns out that the most general solution with this boundary condition is when the dx plus squared, so they have this form. L of x plus some arbitrary function of x plus times dx plus squared times arbitrary function of x minus times dx minus squared. And then we have the dot dot dots, which a priori are non-universal. Okay, these guys are universal. Okay, very good. So this is how an asymptotically ADS3 metric with Minkowski boundary metric looks like. What is the spectrum if we take L and L bar constant? So you can draw a diagram. Sorry? Yes?
Maybe you said it before, but how one obtains this asymptotic expansion for ADS that one's above?
You solve the Einstein equation asymptotically.
Okay, okay.
So and actually, so to arrive at this type of expansion, because this is very general and it with some modification of it holds in arbitrary asymptotically ADS spacetimes. Look at Skanderis from around 2000, maybe 2001 at most, and there are some mathematicians who showed that very generally you can just solve these equations and show that the solution always takes this form. Well, this is in 3D.
Thank you very much.
Yeah. Good. So let's paint the spectrum of this thing. So I'm gonna I'll take L bar constant, and I'll paint L plus L bar in terms of L minus L bar. The reason is that this guy is going to turn out to be mass, and this guy angular momentum. So it's like it. So it turns out that when L and L bar are constant and positive, what you get is this famous BTZ black hole solution. So the Chilean black hole, Bañados, Teitelboim, and Sanelli. This black hole, so this black hole has a horizon, provided that the mass is greater than the angular momentum. Otherwise, there's a naked singularity. So basically, for this region over here, you're going to have these BTZ black holes. You can find them pretty much everywhere in the literature, but okay. You can also look at the original papers. Then, another example of so they're solutions of pure 3D gravity with a negative cosmological constant. Another solution of pure 3D gravity with negative cosmological constant is the global ADS metric, and that turns out to have L equals L bar equals minus L squared over 4. So for that, you have to take the global ADS metric that we wrote in a previous lecture and then transform it to these Fefferman-Graham coordinates. And when you do that, you're going to see that the L's are negative. And then again, with L equals L bar constant and a bit negative, you can also get something called conical defect spacetimes. It's because so they don't have a horizon. You can go all the way where this angle sigma is shrinking. No, well I guess you have to continue appropriately because the Feynman-Graham coordinates are only good near the boundary. But if you work in terms of more global coordinates, what you see for those spacetimes is that they have a conical singularity at the origin, and they sort of lie over here. Anyways, so these are roughly the kind of solutions one looks in. These are solutions of pure gravity that looks in this asymptotically discrete space. Okay. Okay, so now I want to move on to asymptotic symmetries. So let me do it like that. So this is my metric. Okay, so basically I want to say I want the metric to have this asymptotic form where these things are fixed, and L and L bar can change in principle. They just have to stay fun. I mean, if they're on shell, they have to be functions of X plus. So you want to look at diffeomorphisms that leave the form of the metric unchanged. And it's pretty clear from the form of the metric that if you send X plus to any function of X plus, and similarly for the X minus, you're just going to pick up a conformal factor over here, which can then be absorbed into Z. Okay, so what you're basically ending up with are conformal transformations of the Minkowski metric on the boundary. Okay, so actually let me call this function chi left and chi right. So the diffeomorphisms in 3 dimensions that you're getting are this function chi left of X plus. These are 2-dimensional functions, if you wish. The plus a half chi left prime z dz. So this is the z rescaling minus L squared z squared over 2 chi left double prime L minus. So this is one set of diffeomorphisms. I chose them to split them into 2 sets, one that depends on X plus and the other one that depends on X minus. But okay, you just have to switch plus and minus basically. Okay, so then this is plus higher order in Z, which will turn out to be trivial, and this is why I'm not writing them. Now, in order to decide which of these diffeomorphisms are trivial or not trivial, we have to be able to compute conserved charges. And you know, there are many different formalisms to compute conserved charges in. But one that's particularly appropriate for, you know, anti-de Sitter spacetimes is the so-called Brown-York stress tensor, which is really close to this, you know, holographic renormalization procedure. So what is the Brown-York stress tensor? Well, basically what you do, and Brown and York came up with it before holography came around. So basically what you do, you take some spacetimes. So you already know that, you know, the conserved charges are just going to be getting contributions from the boundary. That's a general thing. And what they said is, okay, let's, so they call it the quasi-local energy. So basically you want to look at some region of space-time. It can be finite if you wish, but in the case of the ADS, we're just going to take it sort of close to the boundary. And what they said, let's fix. So it's clear that in order to specify evolution in this region, okay, it's not sufficient to specify initial data. You also need to specify some data on these vertical walls over here. So they specify the metric, the induced metric on the boundary, which I call gamma mu. Okay? Then you take some surface sigma, there's some normal and mu, maybe some sigma that's normal to the boundary. So there's the boundary B, there's a spatial slice sigma. Okay, so what they did, they just wrote down some stress tensor that basically lives on the boundary B of this region, of this space-time region. And this stress tensor is defined in a very holographic-like manner. It's -2 over square root of the induced metric delta as the variation of the gravitational on-shell action as a function of the boundary condition gamma with respect to delta gamma. Okay? So I hope you see that this is very, very similar to the way that we're saying, holographic one-point functions should be computed in IPFT. Okay? Good, and then the conserved charges are simply, integrals over the boundary of the sigma surface. So this is sigma. This is the full sigma. This is the boundary of sigma. So it's a d-2 dimension integral, and then you take, the time like normal to sigma at del sigma, and mu t mu nu into whatever diffeomorphism you're interested in. Okay? So this is how you'd be computing conserved charges in field theory, where you consider the, boundary diffeomorphism. Well, this is the projection of the bulk diffeomorphism on the boundary. Okay, so is the proposal clear? This is the Brown-York conserved charge. Is this clear? How this charge is supposed to be computed?
This expression is for any boundary condition or just for Dirichlet ones, Dirichlet type ones?
Well, as you see, by construction, they impose Dirichlet boundary conditions.
You're right. Okay.
Right? They're saying we're fixing the boundary metric, and then we're varying the on-shell action with respect to that fixed boundary metric. So this is for Dirichlet. Yeah.
Sure. Thanks.
Okay, very good. So now the only thing that we need to specify is what is this gravitational on-shell action, and well, how is it computed? So as gravity, so there's going to be an Einstein-Hilbert contribution. So ddx r square root of the metric in the entire space-time plus. Okay, so now what happens? I don't know how much you guys are familiar with this, but okay, sometimes taught in GR classes. Here we have to do a variation of the on-shell action with respect to the metric, and for that we need that the variation principle be well defined. What does that mean? That means that and you can think about point particles on in a time interval. If you take say m q dot squared over 2. So this is just a point particle. Now, if I want to vary this action, so integral from t1 to t initial to t final of this thing, dt. If I want to vary this action, what I'm going to get? I'm going to get m q dot delta q dot. And now I'm trying to obtain the equations of motion, okay? So this I'm going to write as d by dt of mq dot delta q minus mq double dot delta q. Okay? So when I integrate, then I'm going to get some integral of the equation of motion, which are going to vanish on shell. But then I'm going to pick up this boundary term, which is proportional to delta q. This is a good variation principle in the sense that I'm going to get that delta S is equal to 0 if I'm keeping the boundary conditions for Q fixed at the two endpoints of the interval. However, if delta S happens to, on shell, happens to contain both delta Q and delta Q dot, which you can easily get if instead of writing this, you write M Q double dot Q or something like that. Which has the same equation of motion. If you do that, you're going to get a delta S that on shell depends on both delta Q and delta Q dot, and then you don't have enough freedom to fix both Q and Q dot at both ends of the interval. That's an ill-defined variation principle. So basically what happens with the Einstein-Hilbert action, it's basically of this form. So when you compute its variation, the variation of the on-shell action as you vary the boundary condition, you find both delta Q, which is basically delta of the boundary metric, and delta Q dot being the normal derivative of the boundary metric. And those guys you don't want, so you need to add a boundary term, which is called the Gibbons-Hawking term, in order to cancel those variations. Okay, and this term, so it's a boundary integral, d minus 1 x. So ddx, this is on the entire manifold M. This is only on D. Okay, and it's built from the extrinsic curvature of the boundary into M. I don't have time to explain what this is, the extrinsic curvature, okay, but there's a way to compute it. This K is just the lead derivative of the induced metric on the boundary with respect to the normal to the boundary. You can, for example, look at Walt's book and you're going to get full detail about it. Okay, so you have to add this, and then in principle, so this whole thing now has a good variation principle. But in principle, you can add anything else that depends just on gamma. So any boundary counter term that depends on just the induced metric is also not. It's going to also have a good variation principle. And in the case of ADS, because our boundary is going to be at infinity, and we're going to get all these large distance divergences, it's good for us to have some freedom to play with these counter terms. Okay, so this is how this thing is computed. So the renormalized Brown-York stress tensor that you get from this action takes a form that's roughly, yeah, so it's K nu minus gamma mu. Okay, so it's built from this extrinsic curvature, and then this counter term, you're going to take it to be a boundary cosmological constant, so it's going to be proportional to gamma mu, and then you pick the coefficients such that the divergences disappear. Turns out you can do that. So at the end of the day, the Brown-York stress tensor renormalized is just going to be L and bar 0, 0 in plus minus constants. Okay, so in principle you have to compute this extrinsic curvature. It's not a hard computation, but I did promise I would talk about TTbar, so let me skip that. It's done in very many textbooks, and this is what you get for the renormalized stress tensor. And then for the charges, well, you just plug in this guy over here into the diffeomorphisms, which asymptotically are like this. Actually, these terms you don't, they vanish as z goes to 0. So at the end of the day, the conserved charges, you're going to get Q is equal to the integral over the sigma of chi left of x plus and of x plus. And then you're going to have a similar term with chi right of x minus L bar of x minus. Okay? Those are the conserved charges. Is it clear so far?
Yeah.
Okay, very good. So, in particular, notice that you get an infinite number of conserved charges, right? Because now you can split this chi left and chi right into Fourier modes. Let's say, so we're in global ADS, asymptotically global ADS. We have a full cylinder. It's like that picture over there. So for each Fourier mode of this guy and of that guy, we get one conserved charge. We get an infinite number of conserved charges. So this is good. This is what we're expecting. The other thing that we were expecting is that the algebra of these conserved charges is the Virasoro algebra. So to compute the algebra, okay, so let's see. So you see the matrix. This is perfect, and you even see the charges. Okay, this is fantastic. So if you want to compute the conserved charge algebra, so you want to take two diffeomorphisms of that sort. Let me call one eta and the other one xi. I'll just do it for the left movers, but you can also do right movers and left with right. But this is just for simplicity. Sorry, I forgot. There's a factor here which eventually is important to get everything right. It's 1 over 8 pi g LADS. But okay, anyways, to compute the charge algebra, what do? Sort of by definition, this bracket is the variation with respect to the symmetry associated to Xi of the charge associated with it. Okay, this is what the charge commutator does. It gives you the symmetry transformation. And by this formula, so let me just do the left. I'm going to get 1 over 8 pi GL integral d sigma d C left of L of x plus, right? So the charge associated to eta is going to be given by this integral with the chi eta left of x plus. So the function associated to the diffeomorphism eta, it's some function of x plus. And then when I want to see what happens to this charge when I add to the diffeomorphism Xi, that function is left alone, it doesn't react. But the background metric, when I add to the diffeomorphism, in principle is going to change. Correct? Because when I add to these guys, they act on the subleading term, so delta Xi on the background function L in general is going to be non-zero. Okay, but this is the charge algebra, and actually this guy, so you just act with that diffeomorphism, which you can't see, but you presumably wrote it down. This diffeomorphism over there, you act on it on the full background metric, and you read off from the derivative how L changes. It changes like 2L function Xi prime of x plus function Xi L prime of x plus, everything is of x plus, minus L squared over 2 chi triple prime Xi left. Okay, so that's the change in it. And now, okay, one can have fun manipulating this. So you plug all of this in here, and now let's integrate by parts. So we take this guy plus one of these guys, and then integrate by parts to put the prime on the chi eta. So what we're going to get is 1 over 8 pi GL integral d sigma. And now we don't have L primes anymore. So we have L chi Xi prime chi eta minus chi eta prime chi Xi. And then we have minus, we have the homogeneous term S squared over 2 chi Xi triple prime chi eta. Okay? So this is the answer for Q eta and QC. Now let's pick a basis of Fourier modes on the cylinder. So if we pick chi eta, let's pick chi eta to be e to the I m x plus, and chi Xi to be e to the I n x plus, so just some particular basis elements. Then we have, Qm with Qn, I'm relabeling them, equals 1 over 8 pi GL. And now what am I doing? This is going to give me In minus m. And then I'm going to get e to the I m plus n x plus into L of x plus, and that is going to be Qm plus n. So what I'm picking up is minus I minus n Q m plus n. Sorry, it's without this term because I absorb it into the Q. And then I have minus L over 16 pi G. And then this guy is going to be IN cubed. And then you see that I have no L, so basically this is going to give me a delta function of M plus N. And then this is going to be, so plus IM cubed, which is minus IM cubed delta M plus N times 2 pi from the sigma, something like that. Okay? And then, lo and behold, you simplify all of this, and this is, you know, then you multiply by a factor of I to get from Poisson brackets to commutators, and what you found is precisely the Virasoro algebra. You see, Ln with Ln is n minus n and n plus n with the central extension, and then you can read off that the coefficient of m cubed in the Virasoro algebra is c over 12. This is going to be L over 8g. So C is 3L over 2G. You get a Virasoro algebra with precisely this central extension. Okay, so this is considered a great success of the asymptotic symmetries because you know, usually in conformal field theory, the central charge is not something that's super easy. I mean, it's standard, but you have to, you know, normal order, you have to take care of divergences, regulate them, blah, blah. It's a quantum computation. Here, you're just doing a classical gravity computation, and it's giving you this central extension. So it's a quantum effect in the CFT that's reproduced as a classical effect in gravity. And, you know, whenever you have a string theory realization of a DS3 CFT2, like the original D1, D5, and so on, it turns out that the central charge precisely equals that microscopic central charge. So this is the gravity way of calculating it. Another thing to note is that, okay, so this is depends on LADS. By G Newton in 3 dimensions is nothing but the Planck length. So since you're in the classical gravity approximation, the central charge is much, much larger than 1. So you should think of C as N that we were talking about before. It's the number of degrees of freedom. It has to be very large in order for your classical gravity, arguments to work. Okay, so everything clear so far?
Yes.
Okay, so you're supposed to be excited because we managed to reproduce this infinite dimensional, two-dimensional conformal group from a pure classical gravity calculation, and you said that you need asymptotic symmetries. These are not isometries of any ADS. You couldn't have an infinite number of them. Okay, there's one last thing that I wanted to do. So I'll take a break before the TTbar, but let me do one last thing here, because I promised a microscopic interpretation of the entropy of BTZ black holes. So as I said, BTZs are obtained for constant L and L bar if they're positive. And for that, I should show you, so as it turns out, in two-dimensional CFTs, there exists a universal formula that counts the degeneracy of states at sort of sufficiently high energies. It's given by a universal formula called the Cardy formula. And that formula is computed from something called modular invariance. I'll explain in 1 second. But in order to derive it, one needs to know another universal result in two-dimensional CFTs, which is, in which also the central charge appears, which is the Casimir energy of the vacuum on the cylinder. So what happens is that, okay, CFT on the plane, okay, you have zero energy for the ground state, there's no problem. But if you put the theory on the cylinder, because of the boundary conditions and so on, there's some quantum effect, and actually the energy is slightly negative, and in 2 dimensions, it's given by a universal result. so if you take a course on two-dimensional CFT, so if you look at the De Francesco book and so on, they give you a derivation of that from purely CFT perspective. I haven't done 2D CFT, so I'm just going to read it off from the bulk, because actually this holographic renormalization procedure, the Brown-York, does know about the sort of correct value of the energy in the CFT. It doesn't give you the energy up to some arbitrary constant, it actually gives you the energy. So it's sufficient to just look at the energy of the global ADS vacuum to be able to read off this Casimir energy. And as I said, the ADS vacuum is obtained for L equals L bar equals minus L squared over 4. And when you plug that into the energy, E ADS vac, well, it's going to be so 1 over 8 pi GL integral d sigma L plus L bar. This is what the energy of the vacuum is. And this guy, as I said, each of them is minus L squared over 4, so this is L squared over 2 times 2 pi. So you're going to get minus L over 8G, which is minus C over 12. Okay, so this is EVAC, it's the Casimir energy, and I'm going to use it in 1 second to derive for you this kind of formula. But okay, this is a quick and dirty gravity derivation for it. If you know CFT, you can also just derive it the right way. Okay, so now let me tell you about Cardy's formula. It's very simple. So so let's look at the partition function of the theory at finite temperature. So I'm considering the theory at some inverse temperature beta, and is the theory on some circle of size R. So by definition, the partition function is traced over the Hilbert space of the theories on the size R e to the minus beta h. Okay, and this trace can actually be computed via the path integral by just computing the torus path integral of the CFT. You know, where I take space, so the size of space is R, and then I go an amount beta in Euclidean time, and then I have to trace. So okay, so here I have a circle. This is identified with that, and this is identified with this, because I also have to, you know, compactify Euclidean time on this period beta, because I'm taking the trace. Okay, so this is completely standard. Then the next step is to simply note that since I'm just computing a Euclidean partition function, from the Euclidean point of view, I could be calling this time and this space, or this time and this space. So Z of beta R is equal to also Z of R beta, depending on how I interpret time. And then, because my theory is scale invariant, actually this only depends on Z of beta over R. Okay, it cannot depend on any scale, so it can only depend on the ratio of scales. So now one normally sets, you know, this the radius of the circle to be 1, so circumference 2 pi, and one gets from this relation, one gets that Z of beta over 2 pi is Z of 2 pi over beta, or if you rescale, you get something else. Okay. So the partition function at small temperature is related to the partition function at high temperatures via this modular invariance is called. And now one can actually use it to derive this universal density of states at high temperature. So basically what you want to compute is Z of beta at high temperature. So high temperature means beta going to 0. So I'm using this is Z over 4 pi squared over beta, which I'm going to call beta prime, which is consequently going to infinity. So this is 0 temperature. When I'm going towards, when beta prime is going to infinity, basically only the ground state, the lowest energy state is going to give the leading contribution. So this thing is going to be approximated by e to the minus beta prime E0, EVAC. Okay? But the EVAC is minus C over 12, and beta prime is 2 pi squared over whatever. So this is going to be 4 pi squared over beta C over 12. Okay? In the limit beta goes to 0. Now, so I go into the high temperature picture, and I want, so the partition function can be written as e to the minus beta times the free energy. And from here, okay, let me, it takes me time to do all these calculations, so let me just jump over it. So from here, you get the free energy is minus pi squared C over 3 beta squared, and so on. And then, which is also known as T squared over here. And then you use dF is minus S dt. And then you also compute the energy as F plus Ts. So okay. So the, well, should I give it to you as an exercise? Anyways, so okay. Okay. So what you find is that the energy is minus this, and then that the entropy. So from dF by dt, this is just going to be 2 pi squared C over 3T, and then you write T in terms of the energy. Okay, so this is a bit boring, but at the end of the day, what you find is the famous Charlie formula, which is that the entropy as a function of the energy is 2 pi C over 3T. Okay? For E much greater than C. Okay? So this is a universal formula for the density of states in any CFT. You just need the center charge, and it's a function of the energy of those states. And now, so how about the microscopic interpretation of the BTC formula? So remember we discussed in the first lecture how black holes seem to behave as thermodynamic systems with an entropy given by the Bekenstein-Hawking formula, which was the area of the horizon divided by 4g newtons. Now, for this particular black hole, so the black hole for L bar constant, you can just compute what this formula is. And then L and L bar are related to, well, let's take them to be equal because let's say that the black hole is not rotating, so then they're equal. So L is basically the energy up to some 3 factors. And then you can basically compare this formula to this formula. When you write L in terms of the energy and the central charge, you write it in terms of the ADS lengths like this, and you find they perfectly match. So the Bekenstein-Hawking entropy of the BTC black hole is precisely the entropy in a CFT with central charge 3L ADS over 2G. Okay, and this basically provides a microscopic interpretation for the BTC entropy. What are the microstates of the BTC black holes? Well, they're basically, vibrating excitations at finite temperature in the dual CFT. So the black hole is a thermodynamic object. It has a temperature. Its temperature is the same as the temperature of the dual CFT. And its entropy, you cannot count it in gravity. It's not made out of things that you can see in gravity, but in the CFT, it's just the standard statistical entropy of this thermal state. Okay? And there's a perfect match. I'll let you do the perfect matching of the coefficients because I don't have time, but it's a very acute and standard computation. Okay, good. So, so far so good. So now I have maybe 40 minutes left and the full TTbar to talk about. So I wanted to ask the moderators what, what is the break and the overtime plan?
Well, you can talk as long as you want. It's loud.
Okay, it's up to you. I can. It's true. I have to leave before 6, but that's that shouldn't be a problem. Do you guys want a break or you don't want a break?
Maybe I think it's a good idea to maybe take a 3-minute break before you jump into TTbar.
3 minutes. You see, okay, very good. So during the break, if anybody has any question about this, please ask.
This meeting is being recorded.
Okay, which was supposed to be half of my course. Okay, but now you're ready to understand it. Okay, so as I said in the first lecture, sort of the motivation to study this TTbar deformation, at least for me, comes from holography. It basically comes from trying to understand holography beyond ADS-CFT, some non-ADS spacetimes. And one way that you can think about approaching this problem, there are many ways, but one way that you can think about it is that, as I said, you derive ADS-CFT from this near horizon decoupling limit. So that's on the gravity side. You focus upon the throat, and then deep down the throat, so as you take the energy to 0, you find these ADS spacetimes, and only excitations in the throat survive in that limit. What if, sort of, many of the other examples, okay, there are few examples of non-ADS holography that string theory provides. They're mostly for spacetimes that you don't particularly care about, but these examples exist. And they usually work as this sort of, okay, at least some class of them works like you have an intermediate decoupling limit. So here is asymptotically flat space. And sometimes you can take an intermediate decoupling limit to some non-ADS spacetimes, to some non-ADS spacetime that's intermediate. And then, if you take the energy even lower, you're going to end up with the ADS that you have in standard ADS. Okay, so there exist examples in string theory that do this. And sort of this non-ADS spacetime that you have over here is given by a non-normalizable deformation of this ADS that you have deep in the throat. Okay, so that's a setup. So what's, roughly speaking, the dual picture for this? Well, ADS is dual to a CFT, so you have a CFT over here. And then the fact that you have a non-normalizable deformation of your metric, of your fields, and so on, that means that you've basically turned on what would be the analog of phi 0, right? Of the non-normalizable mode of your fields. So that's adding a source for an irrelevant operator, okay? So you're deforming the CFT by some irrelevant operator. However, this irrelevant flow must be very, very special because in the deep UV, so here you have another decoupling limit. What the decoupling limit suggests is that the theory that you obtain over here is going to be UV complete by itself. So this theory, whatever is dual to this non-ADS spacetime, is just because it's obtained from a decoupling limit, or so you believe, it's going to be something that's UV complete. But that's not going to be a CFT because this is not an ADS spacetime. There's some other type of theory. And therefore, this irrelevant flow has to be incredibly special because usually when you add an irrelevant operator to a theory, well, first of all, you cannot track it down. You can compute maybe a couple of orders in perturbation theory, but then you have proliferation of all sorts of counter terms and you just completely lose track of it. So they're generally intractable. That's still true here in general. And more often than not, they lead to theories with a cutoff, which means if you try to go at higher and higher energies, at some point the theory stops making sense. You have to add new degrees of freedom. What this picture suggests is that maybe that's not the case over here, and then just go all the way to the UV, and you find this other theory. Okay, so that's just a suggestion. It's not that one has a very good handle over this. But so UV complete. But in the examples of non-ADS, non-CFT that one has, so one example has to do with the non-commutative version of super young meals and some spacetimes with some ugly asymptotics. I can say more about it. So this non-commutative super young meals, there's a very beautiful paper of Zyberg and Witten that studied from all possible, and that you can think of as a series of irrelevant deformations of n equal to 4 super young meals, which is a CFT, which are like hugely finely tuned, and they conspire to give you something that's unique. Okay, and that's the picture for that spacetime. Okay, so the conclusion of this blah 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 is that for this non-ADS holography purpose, we're interested, or at least I'm interested, in irrelevant deformations of CFT that lead to UV complete theories. And the problem is that, so they have to be very special, and the problem is that irrelevant deformations in general are completely intractable. So what are you going to do? And this is where TTbar comes in, and it's nice, because TTbar is precisely this type of, it's an irrelevant deformation of 2D theories, say in particular 2D CFTs, that give you some theory that appears to be UV complete. It's not a CFT, it's something that's non-local in the UV, intrinsically non-local in the UV. So TTbar has some dimensionful coupling, which we call mu, which has dimension of length squared. Good. So it's non-local at this scale, and but it's completely solvable. So that's the holographic motivation for studying TTbar. There are many other motivations. So the reason that at some point a few years ago there was some sort of boom in TTbar is that actually this deformation has applications in many different areas of theoretical physics. There's also, so TTbar was proposed by Smirnov and Samolochikov, or people from the, say, integrability community. So integrability into the QFTs. So the question was one about, can you classify all the integrable two-dimensional QFTs? It was some sort of S-matrix bootstrap problem. Here is an S-matrix. They could construct S-matrices, integrable S-matrices, and they were asking to which theory do these belong, and they found one interesting class of theories for this TTbar. Not only integrability, but also QCD. So even before this works, which were, let's say, in 16, there was some very beautiful work by Dubovsky and collaborators who are trying to understand the QCD string by starting with just the normal fundamental string, which was infinitely long, and trying to write it in static gauge. And basically, I mean, it wasn't TTbar back at the time, but they discovered much of the physics. So it's a very beautiful paper called Solving the Simplest Theory of Quantum Gravity. So, but okay, then they had some programs. So this turns out to be very good at computing, energies of these strings and comparing to lattice simulations. So So TTbar is not just in holography; it's also in all these other subfields. I won't have any time to talk about this, but please know that it's there. And it's actually quite interesting. Okay, so what is TTbar? Well, it's a special case of the so-called Smirnov-Samolochikov deformations. So what is this Smirnov-Samolochikov? Basically, they say the following. Suppose you have a two-dimensional QFT, and you have some conserved currents, two conserved currents, JA and JB. Then you can construct an operator, which is the Smirnov-Zamoyski operator, or JA-JB, which is the coincidence limit. So y goes to x of, epsilon alpha beta, the alpha component of JA, the beta component of JB, antisymmetries, and so this is of x, this is of y. So they basically were able to show that the singularity structure of this operator product, of this particular linear combination of the currents, is such that you have some operator that's well defined in this limit, which they call, we're going to call it the Smirnov-Zamoyski deformation, plus everything else is total derivative. Okay, so they managed to define some operator, and this operator has some very nice properties. As it turns out, its expectation value factorizes in the vacuum and in energy eigenstates. If you want to understand the details, just look at the Smirnov-Zamoyski paper. Okay, good. So what is TTbar? Well, for TTbar, you just take these currents. Okay. No, sorry. Let me say what the deformations are. Well, the deformations are simply you take some theory, say you can take a CFT, but it doesn't have to. And then you start adding this operator to the action. Okay? And the deformation is defined as ds, the action by d mu is integral, d2x of OJA JB theory at mu. Okay, so you start with your undeformed theory, you add this Smirnov-Zamoyski operator to the action, then in the deformed theory, you recompute the currents, which are going to depend on the parameter mu. You recompute the operator and you add that operator to the action and so on. Okay? So one nice thing about this construction is that first of all, your operator is defined at all couplings. And sort of non-trivially, it turns out that this deformation, if you do the deformation in this way, you can actually you can actually track it down up this flow in coupling space. So this is not an RG flow. This is a flow in coupling space. You're changing this new parameter of the flow. Okay. Good. So that's the deformation. Now TTbar is simply you take, and of course if these currents have dimension greater than 1, then the corresponding operator is going to be irrelevant, and this is the case that will be of interest to us. So we're going to be interested when the currents are components of the stress tensor. So the TTbar operator is defined as epsilon alpha beta epsilon gamma delta T alpha gamma T beta delta. Okay, so some particular antisymmetric combination of this. Okay, this is what it is. You can rewrite this, okay, up to some numerical factor. You can rewrite it as, T alpha beta minus T gamma gamma squared. Okay, by just using properties of epsilon in 2 dimensions. And you can see pretty easily that this is not TTbar. So normally when you're in a 2D CFT, this is Z, Z, and upper Z is lower Z bar, so this would be TZZ, TZ bar, Z bar, which is called T bar. So this term would be TT bar. And then in 2D CFTs, the trace of the stress tensor is 0, so this is true. But once you do the flow, actually you're going to generate a trace for the stress tensor, so it's not going to be TT bar all along the flow. It's only in the CFT. But this name stuck, despite people like, I think Cardi tried to change it to call it the T, but it doesn't sound as nice as TT. Okay, good. So this is TT bar, and there are indications that so this defines for you the flow at arbitrary mu. And sort of the interesting claim is that this guy is going to end up in some sort of UV complete QFT at finite mu that's going to be non-local at the scale, square root of mu or something like that. Okay, very good. Any questions about what I said so far? Is this business about the irrelevant flow clear?
Mm-hmm.
Okay, I mean it's something that unlike what people normally do in QFT, but seems to go. Yeah, another important thing for this community is that if your original theory is integrable, then TTbar preserves integrability. So then you can use things like thermodynamic beta ansatz and so on in a different theory, which is nice, which was also present in this paper by Lewowski. Okay, very good. So what does one normally? So I said the TTbar is solvable. What do I mean? So people, okay. So the original thing that people solved, that Smirnov-Samarkov solved, was the spectrum of the deformed theory in finite size. So as it turns out, if you know the spectrum, finite size spectrum of the original theory, you can actually solve for the spectrum of the deformed theory. So that's one thing. And from the spectrum, you can also study thermodynamics and things like that. I'm going to review it. But by now, people have, you can also do S matrix. So that was also in this paper. So the S matrix of a TTbar deformed theory is just a phase that depends on momentum, a universal phase, times the S matrix of the undeformed QFT. So pretty much, it's a theory in which people have now more recently looked at correlation functions, which are a bit more complicated. But in each case, what you find is that the deformed TTbar deformed observables are related by some simple but non-local procedure to the observables of your original theory. That seems to be the leitmotif. Okay, so that being said, let me tell you about how you compute the spectrum, the TTbar deformed spectrum in finite size. Good. So okay. So people really like to study this theory on the cylinder. So you put this two-dimensional QFT, TTbar deformed QFT, on the cylinder, and then it's just some quantum mechanical system. And then you can ask about the flow of the energy eigenstates and of the energy eigenvalues. Okay, so remember, okay, if I then you'll be able to see it. Do you see the definition of the theory? I think you see it, right? Okay. Okay, so you have this incremental definition where this is TTbar. Okay, so as I was saying, you can just do quantum mechanics cartography theory to study this theory on the cylinder, which is supposed to be some system with some discrete set of states, and so on. So as you well know, so I'm starting with the theory at mu, which is somewhere here, and I'm going to the theory to mu plus d mu. So I'm looking at some energy level, which I'm going to call n, which depends on mu. I'm at finite size r, and I want to compute d by d mu of this energy. Okay, and I'm calling the energy eigenstate n like this. It's the instantaneous energy eigenstate in the theory at coupling mu. Okay, so this as you know, this is just given by the expectation value of the deforming operator. So now I'm taking a sort of a Hamiltonian perspective. So I'm going to do a spatial integral of the TTbar operator. So it's going to be the expectation value in the nth energy eigenstate of the deforming operator. Okay? Because the deformation of the action is that, and then you can relate it to the deformation of the Hamilton. Is it clear what I'm doing? Quantum mechanics, perturbation theory, instantaneously at mu. Okay? And the goal is to obtain a flow equation for the energies. So now what one does, one uses the factorization of the eigenstates. Okay, so I have T. So when I compute what this gives me in T sigma coordinates, so actually tau sigma, so I go to Euclidean space and tau is Euclidean time, then TTbar is T tau tau T sigma sigma minus T tau sigma squared. Okay, and as I said, this guy factorizes in energy eigenstate. So I'm going to have this n minus n T tau sigma n squared. Okay, this is using factorization. And now, the name of the game is to actually replace these expectation values by the instantaneous energy, momentum, and so on. So as you well know, so here I'm also integrating over the circle. So I'm picking. Well, this is just going to be constant. Everything is constant because these are diagonal elements. So, well, the expectation value of the TT component of the stress tensor is just going to be the energy divided by R. So, and in Euclidean, this is minus E over R. T sigma sigma turns out to be related to dE by dR. So, this is the energy of the nth level. And T tau sigma is the momentum density. So, this thing is going to be P over R, Pn over R. Okay, so you're basically just getting some flow equation for each energy level in part that comes basically from factorization and being able to write in terms of everything in terms of En. Yeah, so you're just getting a flow equation for each energy level in part. Let me set the momentum to 0. You can do it for general momentum too, but this flow equation is something like d mu En is E dEn by dr. This is all there is. Okay, if I neglect the momentum. This is known as Burger's equation, and one can just solve it. And it turns out that the solution, so En of mu r, turns out to be En of 0 r plus mu En. And r. Okay, so if you take this ansatz, so these are basically the undeformed energy of the theory on a circle of circumference r plus mu times the energy. If you take this ansatz, you can just show that you're satisfying this equation. Okay, so this is all there is. If you know the spectrum of the undeformed theory, this is mu equal to 0 for arbitrary finite size, then you know the spectrum of the deformed theory. Okay, and this is a very powerful result. Now, people like to do TTbar deformed CFT. One reason is that you know exactly the R dependence of the theory on the cylinder. So this is not something that I discussed, but it's true that if you put a CFT on the cylinder, then the spectrum of energies that you get is CFT on the cylinder is going to be related to the conformal dimensions delta as 2 pi delta divided by the circumference. Okay, So in a CFT, this is how the E0, this is the E0, depends on R. So then you can just solve, since you have E mu is equal to 2 pi delta over R plus mu E mu, something like that. You get a quadratic equation for the energy, for the deformed energy, that you can very easily solve. And the solution is En is R over 2 mu square root of 1 plus 8 pi mu delta n minus c over 12. Sorry, I forgot something. Here, the energy is actually, there's this shift by c over 12 that we just discussed. Because the conformal dimensions on the plane, and then on the cylinder, you get this extra Casimir energy. So it's there and it's important. Okay, so that's the energy divided by R squared minus 1. Okay, so this is the full answer for the spectrum of deformed energies of the TTbar deformed CFT on the cylinder. You know it for each delta. And it has some peculiarities. Okay, so first, please note that when you take mu to 0, you just end up with the CFT energy, because this mu cancels with that mu. Another funny thing that's happening is that, okay, so your lowest dimension operator in the CFT is the identity, which has delta equal to 0. So you actually see that for the ground state, you have 1 minus something times c over mu c over R squared. So if R is too small, then actually the square root can become imaginary. And the minimum value of R that you get from this, you're going to get imaginary energies for the vacuum if unless R is greater than this critical radius, which is square root of 2 pi mu c over 3. Okay, so basically what this is telling you that if you have this TTbar deformed CFT, you simply cannot put it on a cylinder whose radius is smaller than this RC. This is very much okay. So this behavior is very much unlike the behavior in a local theory. So for example, if you have a local theory, you can look at the behavior of the energies of, for example, the ground state energy on a very, very small cylinder as R is going to 0. And then what you're supposed to see is basically minus C over 12R, because that's saying that the UV of your theory, which you're seeing as R goes to 0, is governed by a CFT. And then you're just getting the CFT result. Here you see that you can't even take R to 0. So the behavior of this theory in the UV, it's clear that it doesn't have the behavior of a CFT, because as you take R to 0, you don't find the expected CFT result. Okay, so this is one way to see the non-locality of the theory. There are many other ways. There's a way to see it from the S matrix, but basically, yeah, this theory is really non-local at the scale set by the deformation. Okay, good. So now you have the deformed energy as a function of the undeformed one. Now, yeah, so basically what you're finding is that each energy level in the theory, so if this is mu at mu equal to 0, you had some energy levels, and then each energy level is just getting smoothly deformed according to this form. That's all that's happening. But you see, you have to check it, but it's true that energy levels don't cross, and then the number of energy levels also doesn't change, because they're just mostly deformed. So this last fact is basically allowing you to compute the entropy, the degeneracy of states in the TTbar deformed CFT. as a function of the energy. Basically, because you know that in the undeformed CFT, so if you want to compute the entropy, say at high energies, and you see from here that high energy is the same as large delta in the undeformed theory. So the number of states in the deformed theory, because these guys just get smoothly deformed, is going to be the same as the number of states in the undeformed theory at the corresponding and undeformed energy E0. Okay, because you're just counting the same number of states. And this guy for E0 large enough, we just reviewed the fact that it's given by Cardy's formula. So this is 2 pi square root of C E naught over 3. But E naught is going to be 2 pi delta minus C over 12. Okay. Well, there was a 1 over R, but there's another R, so I think 1 is fine. There's not going to be the 2 pi, maybe. Yeah. Okay. So this is what the Cardy formula is in terms of delta instead of energy. And now, basically, in order to know S of E in the deformed theory, you just have to replace this delta minus C over 12 in the undeformed theory. You want to know it as a function of the deformed energy. So you just have to take this guy and replace it by its formula in terms of the deformed energy. And that's a quadratic formula. So the end result that you have is 2 pi square root of C over 6 pi ER plus mu. Okay. TTbar deformed CFT. Okay. Everybody's very quiet, so let me ask if it's clear what I've done so far.
Mm-hmm.
Okay. So I've basically obtained what the density of states at high energy is in this TTbar deformed CFT. And what's interesting about it, so this square root of ER is basically Cardy behavior, but at very high energy, you see that S of E is proportional to E, and this is known as Hagedorn behavior. And Hagedorn behavior is something that appears commonly in string theories. So you also get it if you try to count, compute the partition function of or count the number of states of strings at high energies. They also have Hagedorn behavior, and basically it tells you that you have a maximum temperature in your theory. Why? The reason is that so S of E is E. Let me put equal E times beta Hagedorn, so some constant. The reason is that if you're trying to compute the partition function, which is E to the S, the number of states, times E to the minus beta E, sum over E. If E goes like some constant, if S goes like some constant times E asymptotically, you see that if beta is smaller than beta H, which means that the temperature is larger than 1 over beta H, then the partition function will diverge because you're going to be summing exponentials with a positive coefficient times E. Okay, so the partition function doesn't make sense. So basically you have T smaller than T Hagedorn, which is 1 over beta H, and here you just read it from here. So what is it? Beta H for TTbar. Beta H for TTbar is square root of 2 pi mu C over 3. Okay, so this is very characteristic of TTbar. It has this Hagedorn behavior in the UV, which is also the kind of behavior that's characteristic of strings. So it really smells like this TTbar has to do something with strings, and I mentioned that people interested in QCD strings were interested in it. So maybe you can see a connection. Actually, there's a pretty direct connection. If you try to solve, you take a free boson, so d phi squared in 2 dimensions, and you try to solve the equation for the action. So you try to solve this equation, assuming that the action only depends on d phi squared because of breaking Lorentz invariance and so on. Then what you find is the TTbar deformed free boson. The deformed action looks like 1 plus mu d phi squared minus 1 over 2 mu. This is the TTbar deformed free boson, which turns out to be nothing but the action for a string that propagates in 3 target space dimensions in static gauge. So there's a pretty direct relationship to strings. And okay, what I was saying is that you also see it in the entropy. Okay, good. So on my negative time, I'm going to tell you about the holographic interpretation of TTbar. So now you have a few facts about it, and I'll tell you how you can reproduce it. Unless there are questions. Are there any questions about this field theory discussion?
Hello?
Yes. Yeah.
So I want to ask, like, when we perturb this field theory with this TTbar deformation, how this perturbation actually sends the stress tensor of this deformed theory in comparison to the original theory?
Sorry, how do I didn't hear the...
So when you perturb this CFT with TTbar deformation, so how does the perturbation sends the stress tensor of the field theory in compared to the original theory?
The stress tensor. You're asking about the stress tensor?
I mean, like,
sorry, I can't hear you. The sound is not very good. You're asking about the stress tensor.
I will type in the chat box. Actually, my
no, but it's not useful. So you see the stress tensor. So for example, I give you an example here. Mu d phi squared minus 1 over 2 mu. This is the Lagrangian for a TTbar deformed free boson. Okay? So you see it has an infinite expansion in derivatives of phi. Only first derivative, but there's an infinite expansion. And the stress tensor, you just compute it using the usual Noether procedure. So you're just going to get some functions, some similar with square roots and blah, blah. You can compute all the stress tensor components.
So like when we do for a coordinate transformation, like from Z to Z bar, we write TZ transform as some factor TZ plus C by 12 into some factor. So can we apply also similar transformation in the deformed CFT?
Yeah, so this is a very interesting subject, and it was originally discussed in this paper by Dubovsky. So what's happening? Okay, so one thing that's happening is that you can think of this TTbar as looking at your original CFT through the prism of what people call dynamical coordinates, which are some coordinates that are related to the CFT coordinates. They're the CFT coordinates plus some shift by the integrals of the stress tensor, something like that. So they depend on the state of the system. And using these coordinates, you can derive the S matrix. You can do a lot of things.
Okay, thanks.
It seems to be true that you can also look at the Virasoro symmetries of your original CFT through the prism of these coordinates. I mean, it's not exactly that, but and then you can get some sort of field-dependent Virasoro. So they're basically things that are parameterized by arbitrary functions of these deformed coordinates, of these field-dependent coordinates. So before we had symmetries associated with arbitrary functions of x plus and x minus. Now we're going to have symmetries associated with arbitrary function of this field-dependent modification of x plus and field-dependent modification of x minus. But how exactly they act, especially at the quantum level and so on. So I wrote papers about the action at classical level, which is sort of already complicated. At quantum level, I don't know. I guess you're asking precisely about conformal transformations, right?
Yeah.
Yeah, so that would be the analog. The symmetries seem to exist. But I don't personally have a full understanding of how to think about them, especially at the quantum level.
Okay, thanks.
Okay, very good. But you see, if you're trying to compute stress tensors and so on, it's okay. It's a bit complicated. This action has an infinite number of deltas. Good. So holographic interpretation. So as you can see from its construction, TTbar is a double trace deformation in terms of terminology. Why? Because the CFT stress tensor, in a holographic CFT, is going to be the stress tensor is a single trace operator in the CFT. So TTbar is two stress tensors, so it's double trace. Consequently, we expect that this holographic interpretation is going to be in terms of some mixed boundary conditions for the dual bulk field, which in this case is the metric. Okay, so we just expect to be changing the boundary conditions on the ADS metric. So let's see what they are. How do you do this? I'll just tell you what the result is. Okay, so remember. But yeah, it's changing the boundary condition on the ADS metric, but it's not changing the ADS-ness of the metric. Okay, so we're still starting with an asymptotically ADS spacetime, which is given by this nice Fecha-Graham function plus non-universal dx mu plus L squared z squared over z squared. Okay, and as we discussed before, so in standard ADS CFT, when you get a CFT on the boundary, the CFT is dual to ADS gravity with Dirichlet boundary conditions, so you're fixing this G0, and G2 is fluctuating. Now, we're adding this double trace deformation that depends on the stress tensor to the boundary action. And as I explained last time, in order to get the holographic dictionary in that case, you do two steps. The first step is a purely field theory step. You just try to express the partition function of the deformed theory, which is a function of the deformed source. So, let me call this gamma 0. I call them gamma for some reason. Okay. So, no, sorry, no. Let this be G0. Sorry. Let me call the metric in which the deformed theory lives, which is the source for the stress tensor, because stress tensor couples to metric, gamma mu. And let me call this actually alpha beta to not confuse them with the mu of TTbar. Okay, so as I said, when you deal with these multi-trace deformations, first you do a field theory step using large N, where you relate the partition function of the deformed theory in terms of some source gamma mu for the deformed stress tensor to the undeformed partition function, so the partition function in the undeformed theory in terms of some source. And this source is some combination of the source and vev over here. Okay, so it turns out that for TTbar, you do this manipulation of the path integral, which I'm not showing you. And what you're finding is that this the relationship between gamma 0 and gamma mu is the following. Gamma mu alpha beta is gamma 0 alpha beta minus 2 mu t alpha beta hat 0 plus mu squared t hat alpha rho 0 gamma 0 rho sigma t hat sigma beta 0, something like that. Okay, so before we had that the source in the deformed theory was the undeformed source plus the VEV of the operator. Here it's a bit more complicated because we also have a term that involves the VEV squared and also the inverse source. Okay, it's slightly more complicated, but you can actually work it out exactly. And also the relationship between the VEVs in the deformed and undeformed theory, they're not exactly equal as they were for scalars, but there's a correction term. I won't write it. Okay. As it turns out, okay, so this is the result of the larger analysis. Now, if I want to get the holographic dictionary, what I should do, I should just use the undeformed holographic dictionary, so just for the CFT, to write this gamma 0 in terms of bulk fields. Okay, the relationship between gamma 0 and gamma mu in terms of bulk fields. And what I see, well, the boundary metric in the undeformed theory is nothing but this G0 over here. So this is going to be G0. This expectation value in the undeformed theory, and the T hat is actually the trace tensor minus the trace T gamma gamma, something like that. This is what T hat is. It turns out that T hat precisely corresponds to this factor G2. So this is just going to be G2. And this is just G2, G0 inverse G6. Okay? Okay, so what's the holographic dictionary in this case? Basically, the TTbar deformed CFT. So in the TTbar deformed CFT, I want to be keeping, this is the source for my deformed stress tensor, and which should be held fixed. And in terms of bulk quantities, it's these particular combinations of G0s and G2s. Okay? So what I'm getting are basically mixed boundary conditions. Where I'm keeping fixed G0 alpha beta minus 2 mu G2 alpha beta plus mu squared distinct alpha beta. Okay? So it's a nonlinear mixed boundary condition that involves G0 and G2. So what I'm doing is that I'm fluctuating. Both of these guys are allowed to fluctuate, but in such a way that this particular nonlinear combination is held fixed. Is it clear?
Yes.
Okay, so it's very similar to the scalar field case, but okay. What's interesting over here, over the scalar field case, is that you see, so I told you that TTbar is a non-local theory, and we can see that in field theory in many different ways, which I didn't show to you. You see, what I'm doing in the bulk is that I'm keeping the same action in ADS3, you know, it can be type 2B string theory with everything. And I'm just changing the boundary conditions for the metric to this mixed boundary condition that I just explained. Same action with the mixed boundary condition for the bulk metric is dual to a boundary theory that's no longer local. So you see, just simply changing the boundary conditions on the bulk theory, if you do it at the level of the metric, is just destroying the locality properties of the boundary theory. Okay? So we're still in ADS. This metric is an ADS metric. But and this is something that I don't know if it's fully appreciated. So especially in AD3, people look a lot for boundary conditions, this boundary condition, the other boundary condition. You know, they try to explore all possibilities. TTbar is an example where, you know, the boundary conditions on the bulk metric are derived from the boundary, because we started with the definition of TTbar in the boundary, and then we derived what the boundary condition on the bulk metric is. And this derivation shows us very clearly that you can get, you know, whereas you may not be, it's not super obvious, because these sort of guys are a little bit non-dynamical, and you don't really see the non-localities, but the derivation from the boundary theory shows you that imposing such funny boundary conditions on the bulk metric gives you a non-local boundary theory. Okay, so I just wanted to make that clear. Now, so one fun thing we can do now that we have the boundary conditions, we can do precision holography. So for example, one thing that we can do is, can we get the, entropy to energy relation for high energy states in TTbar? Can we get the spectrum from holography? And the answer is yes. In order to find it, basically, so you want to study, you want to model. So what I was discussing in field theory was TTbar deformed CFT on flat space. So we basically want the boundary metric in the deformed theory to be Minkowski. So it's going to be fixed and it's going to be eta alpha beta. And then, so we fix this metric to be Minkowski, and then we want to sort of build the gravitational phase space, similar to how we did it for Dirichlet boundary conditions. If you remember, in Dirichlet boundary conditions, we're fixing this metric to be eta, and then we're looking at the most general, G2 that we could have. They were parameterized by this L and L bar. Here we're doing the same, except that we're fixing this particular weird combination, and we're looking for the most general bulk solution that that obeys this boundary condition. And that bulk solution turns out again to depend on two arbitrary functions of something. So I'm going to call them, maybe, let me call them L mu and L bar mu, just to not confuse you. They're not the same as the previous ones. And they depend on what I was referring to before as field-dependent coordinate. So little u is related to x plus, which is just sigma plus t, the TTbar, the fixed TTbar coordinate, as x plus mu integral up to v of L bar mu of v prime dv. They're defined in this way. And similarly, little v is defined in terms of x minus with the u integral and with the L over here. So this is what one calls the field-dependent coordinates. These are the coordinates in which the TTbar dynamics looks just like CFT dynamics. And so you have these two functions, L mu of u and L bar mu of v, that parameterize the phase space. So now, in terms of them, this G0 and G2 and so on, they look kind of horrible. So if you want to look for the horrible formula, I wrote a paper about this with Ruben Monson in 2019. It has Mirage in the title, but we worked all of this out. Okay, you compute the phase space, then you use the stress tensor one-point function in the deformed theory that you know from this analysis to compute energy and angular momentum in the deformed theory, and then you can compute the relationship between the entropy of black holes in the bulk and that energy, and you find precisely this Hagedorn behavior and so on. So you can verify all these TTbar properties from this gravity calculation, and everything is very nice and precise. Like you can really compute everything, but the bulk metric is very ugly because you're fixing this ugly linear combination. Now, if you want some intuition into what this boundary condition looks like, there's actually some nice intuition that comes from a paper by Verlinde, Messey, and McGough. So what's the intuition? If you look at this combination, so remember I told you that if you are in pure gravity, then this term over here, which is not universal in general, but in pure gravity is something like z squared over 4, G2, G0 inverse G2, alpha beta. If you are in pure gravity, it turns out that this boundary condition over here looks exactly like Dirichlet boundary conditions on a surface where well, am I using the same coordinates? Let's hope I'm using the same coordinates as I was using in my paper. Okay. At z equals minus mu over 4 pi g. I might be having z squared actually. Okay, I need to check it, but anyways. So, point being that if mu is negative, which is actually kind of a sick theory, as you can see from the entropy formula. So if you look at the entropy formula for mu negative, it tells you that the entropy becomes imaginary at very high energy, which doesn't really make sense. So actually the spectrum is cut off. Actually the theory with negative mu, so it's a theory with superluminal propagation, and if you put it in finite size, as we want to do over here, actually it has closed time-like curves and all sorts of like problems. But anyways, if you want to get in some intuition in what these boundary conditions are in the special case of pure gravity, you notice that they look exactly like Dirichlet boundary conditions on a so-called cutoff surface, which is minus mu. So if mu is negative, this is going to be some real cutoff surface, minus mu over 4 pi gr. Okay? This is a coincidence as far as I'm concerned, because this, okay. So I was talking about getting a mental picture. So if a slice through the, so you have your ADS, so I'm slicing ADS I'm doing a time slice, and this is the ADS boundary. Then this surface is somewhat lying over here, some finite distance from the boundary, which is fixed by this mu. And what I was saying is that boundary condition, so this is for negative mu, the boundary condition is such that you fluctuate the ADS boundary metric and you fluctuate the G2 term in such a way as to conspire that the metric on this particular surface is held fixed, is just the Minkowski metric. This is what roughly these boundary conditions look like. So you see they're kind of very non-local near infinity. What else did I want to say? Yeah, so what I wanted to say is that, okay, so this coincidence only happens in pure gravity. If you have matter, it doesn't happen. However, some people really sort of like it because they want to think that somehow, yeah, so it has been proposed that the TTbar with negative mu has something to do with the gravity at finite cutoff. And the connection comes precisely from this result in pure gravity, that you get basically Dirichlet boundary conditions. Effectively, in pure gravity, you get Dirichlet boundary conditions at a finite distance in the bulk. How should I say? I'm a little bit confused about this proposal for several reasons. One reason is precisely, so even if I'm happy to do pure gravity, as I said, mostly the CFT correspondences that I might start with also have matter fields, so this coincidence doesn't work. But even if I'm happy to do pure gravity, I don't really understand why one should just, you know, what I showed is that you get mixed boundary conditions at infinity between G0 and G2, whereas their proposal is that they just keep this part of the space-time. I don't understand what happens to this part of the space-time. If you're in exactly pure gravity in ADS3, that's a very trivial theory, which doesn't really have bulk degrees of freedom. So you might say it's fine. You started the affirmative with no bulk, and now it's going to live at a finite surface, fine, but that's a little bit trivial. If you do want to have matter fields, then it's a bit more complicated because, as I said, it's not true that these TTbar boundary conditions are equivalent with the conditions at finite cutoff in that case. So what do? Sometimes people say, so one thing that I didn't say, for the metric you get mixed boundary condition, but it should be clear that for the matter fields, the matter field boundary conditions are unaffected by TTbar, and they're just going to be Dirichlet infinity. So it's not true that you get for the matter fields boundary conditions at finite cutoff. Sometimes people try to enforce that by adding also multitrace double trace deformations for the matter fields. But then I think you completely lose the mapping, the precision mapping to TTbar. But that's me. Okay, and the final comment is also this negative mu. It's a theory that's a little bit delicate, and maybe it can be made sense of, maybe it cannot. So one has to be careful. The reason that I'm keeping all these comments I haven't properly introduced it, but at some point there was some big discussion in the literature about this finite cutoff. So I just wanted to give you my. Okay, good. What are the things? Okay, so coming back to precision TTbar that I like. So I just have these mixed boundary conditions at infinity, and I'm just studying, the gravitation phase space. I can ask about the asymptotic symmetries of the space-time, which are basically going to be the symmetries of gravity with these boundary conditions. And what one finds is that you find an infinite number of symmetries, which are parameterized by two arbitrary functions, one f of u and one f bar of little v of the same field-dependent coordinate. And what's interesting is that if you work in some particular basis, and this we did, so we didn't quite get it in this paper, but then I redid it in the appendix of a paper I wrote with my student, Silvia Georgescu, in 22. You find that the associated conserved charges in some particular basis that you chose satisfy precisely the Virasoro times Virasoro algebra. And that's sort of interesting. So this is a non-local theory, but still it seems to have Virasoro algebra. As I was mentioning like 10 minutes ago, I don't fully understand quantum mechanically how these symmetries are supposed to act. I don't know. So classically, we constructed them in every possible way, but quantum mechanically, I think there's still important questions about how to make sense of them and so on. I mean, there is some quantum mechanical definition. So the way that I think about them is that, you have this TTbar flow out of the CFT. In the CFT, you have Virasoro times Virasoro. And then you can simply transport the Virasoro generators along the flow while keeping the algebra. And how do you do that? Well, in TTbar, you have some flow of the energy eigenstates, which you can control. So this matrix chi is known. And basically, you decide to flow your Virasoro generators in the CFT with the same matrix. That's a definition. By definition, it preserves the algebra. It doesn't quite give you the physical symmetry generators in the TTbar deformed CFT, but they turn out to be just related by some rescaling by the energy in the classical limits. So that's the status. So we think that we can also define them, all along the flow, and we can see them very clearly on the gravity side via this asymptotic symmetry group calculations. Okay, I'm already half an hour over. I'm sorry. So I don't know what you guys want me to do. So in principle, so this is just a double trace TTbar. So the important thing here is that one can do precision holography for it. And in principle, in this course, you've learned the tools for how to do it. All you have to do is understand how to work with multi-trace operators in IPFT. I have prepared, maybe a couple more pages about trying to apply TTbar to understand properly relevant flows. But, given how I'm going, that might take another half an hour or so. And the question is whether you guys want me to go on or I should stop here, which I can also do.
This meeting is being recorded.
So the question was whether there are any questions for this part.
I have a question about the energy level. So when you keep R fixed and you crank up mu, it seems that at some point you get imaginary energy. So is there like a physical interpretation for that?
Well, not here. For mu positive, I don't.
But what about for like delta less than 0?
Yeah, exactly. So this is what I was saying. If in unitary CFTs, delta has to be positive.
Mm-hmm.
Yeah. So the initial spectrum of the CFT is that the identity, which has dimension 0, is sort of the lowest dimension operator. So I'm not looking at unitary CFTs. I'm not looking at non-unitary ones, which could have delta negative. And in that case, the worst case scenario that I have to worry about is delta equal to 0, because everything else has higher delta, and that breaks down when at this RC. And I only need to check the ground state energy because sort of delta slightly positive, but smaller than C over 12, breaks down at smaller radians. People do spend a lot of time in view of this cutoff holography and so on. They do spend a lot of time with mu negative. And then you really have a problem because all the delta large gets imaginary energy.
Okay.
My understanding of what's happening is that the theory is kind of sick. It has these closed time-like curves, and the imaginary energies are just supposed to be some reflection of the fact that the theory is kind of sick. And this has been put forth, this interpretation in some paper of Dubovsky and someone else, maybe Cooper, from around 2013 or 14.
Okay.
But yeah. So people discussing a lot in the case of this cutoff holography, the negative mu case. Yeah, you might just say, okay, this is just not physical. But then there's something sort of cute that happens in the bulk at that point. So the point where the energy start becoming negative is precisely so the energy. So in the case of pure gravity, as I said, this cutoff only works in pure gravity. So the states that you're looking at are just black holes, because you just have black holes. You have conical defects, black holes, and vacuum. So you look at black holes, and basically the energy for mu negative, the energy at which this becomes negative, precisely corresponds to a black hole whose size is as big as the cutoff surface. Okay, so that's a nice thing that's happening. I don't know if it has any deeper meaning, but it does happen.
Okay, thank you.
And then they say that they just cut off all the other energies, which corresponds to cutting off the black holes that are, outside the cutoff. Okay, good. So as I said, I actually have a cutoff myself, so I do need to finish. So as I said, the reason I was interested in TTbar was because of this non-ADS holography, which had this picture with the sequential decouplings, right? There was an ADS over here, and an interesting non-ADS over here, such that this thing was some non-normalizable. Okay, this is the setup that I was interested in. And the TTbar that we discussed, this double trace TTbar, as we just saw, all it can do is it can take ADS3 and change the boundary conditions, but it doesn't change the local geometry. Whereas here, in this interesting, more interesting cases of non-ADS holography, one does need to change the local geometry. So what does one need? Well, what one needs is basically, of course, as I explained in one of these lectures, bulk fields are dual to single trace operators. So these supergravity fields that we're looking at, they're dual to single trace operators in the dual theory, and therefore in whatever is happening here, we can look infinitesimally around ADS and apply the ADS dictionary to see what we're doing, and we need to be adding some sort of irrelevant deformation by a single trace irrelevant CFT operator in order to produce something like that. Okay, so what one would like in order to apply TTbar to this kind of setup, one would like something like single trace TTbar. To explain what single trace TTbar is, I need to tell you. So we talked about what single trace means in n = 4 square meters. That's easy because it's a gauge theory. But here we're doing ADS3 CFT2 and the formations thereof. So I need to tell you what the gauge group that we're talking about is in this case. And so for ADS3 CFT2, so we're looking at realizations of this correspondence inside string theory. And for that, one has the famous D1D5 CFT. So if you guys don't know, there's an old and very useful review by Mandal, Wadia, and I think David from like 20 years ago, reviewing everything about this theory. And then what? Okay, so the realizations of ADS3 CFT2 in string theory, you have to start with a stack. The thing is that you don't just have a stack of these membranes of the same kind. So in ADS5 CFT4 that we discussed, we just had a stack of D3 branes which have a 4-dimensional wall volume theory, and the wall volume theory on D branes it's some gauge theory. In here you have to start with a stack of strings which are these D1 branes, and with some 5-dimensional branes that are wrapped on some 4 manifolds. So let's say this D5 is on some 4 torus. And then, okay, you have some gauge theory, but then you really need to flow to the IR to reach the CFT point, and that flow is untractable. So you lose sort of the gauge theory description. However, it's conjectured, okay, that this CFT, okay, so it's just conjecture that you're going to flow to some CFT, and then the question, but you don't have the gauge theory description anymore. Okay. That's what I wanted to say. And this CFT is the so-called D1D5 CFT, which is nice. It's super symmetric. It may be important, and so on. And when I say D1D5 CFT, it's not just actually one theory. There's actually a full class of theories which are related by, so it's the D1D5 CFT, which is actually a family of CFTs, which are related by exactly marginal deformations. So what's an exactly marginal deformation? It's you take your CFT action and you add to it an operator whose dimension is precisely D, including quantum corrections and so on. It has to be exactly D. If you do that, then you actually don't break conformal invariance. And so you have some parameter lambda here, and there can be several such deformations. So we're going to label them with some I, all the exactly marginal deformations of this CFT. It turns out that in supersymmetric CFTs, you actually do get all these sort of families of theories. So this is what we have here. So the D1D5 CFT, there's actually what we call a moduli space of CFTs, which are parameterized by this lambda I. So I think for T4, the moduli space is 20-dimensional. Okay, and then these lambda I's are like some sort of couplings. Okay, so they're analogous a little bit with the Toft coupling. They're exactly analogous to the Toft coupling that we were discussing in the n = 4 superunits case. But okay, so you guess this one. Now, there's supposed to exist a point in this moduli space of the D1D5 CFT, which is called the orbifold point. Which is supposed to be like a weakly coupled point, so analogous to weak Toft coupling for n = 4. And at this point, the description of the CFT is supposed to be in terms of some sigma model of T4, so some M of central charge 6. You take n copies of it, where n is the number of D1 branes times the number of D5 branes, and you mod out by the permutation group. Okay, so you have some seed CFT, you take n copies of it, of its Hilbert space, and then you quotient by permutations of the different copies of the CFT. This is known as a symmetric product orbifold CFT, and this is supposed to be the description of this D1, D5 CFT at some particular point in moduli space. This description is weakly associated. So in this description, you can actually do computation, so it's nice. And the gauge symmetry over here, so it does have a gauge symmetry. The gauge symmetry is given by permutations of the different copies of the seed. And you see it's a discrete gauge group. Okay? It's given by permutation, it's not a continuous gauge group. Okay? This is supposed to be the weakly coupled point in the CFT coupling space. So it's holographic dual, it's an ADS3 spacetime that's string scale. Actually, people could write down, could study it. There's been sort of recent progress in the last 5 or so years on understanding it. But it doesn't give a nice, place where we can use classical gravity. The sort of the supergravity point is somewhere here at strong coupling. And in order to get to it, we need to deform this orbifold CFT by one of these exactly marginal operators. And what happens is that when we do that, we have to deform by one that actually breaks the symmetric product orbifold structure. Okay, so this is why it's a little bit complicated to talk about this gauge symmetry. So we have this gauge symmetry at the weakly coupled point, but it's sort of hard to get our hands on it at the strongly coupled point, if we want to think of this as the gauge symmetry, but this is sort of the analog. Okay, so all this song and dance was to explain to you what is supposed to be the single trace variant of TTbar, and that's very simple. So if this is supposed to be my gauge symmetry, some symmetric product orbifold, then single trace TTbar is that okay. So if you want to build gauge invariant operators in the symmetric product orbifold CFT, the simplest thing that you can do is you take some operator in the seed. So in this CFT n, in the ith copy of the CFT, and then you sum over copies. So, I don't know if you saw. Okay. So this is how you build gauge invariant. So obviously this thing is going to be invariant under permutations because you've summed over all copies of the CFT. That's the simplest gauge invariant operator. So. And this thing is single trace because I'm having a single sum. So, so given this, a single trace TTbar is something that's defined in a symmetric product orbifold theory, and I'm just summing over the copies of the theory TTbar in copy I. That's all there is. So that's very nice, and then you can study its properties. So single trace TTbar, you can study its partition function, you can compute a lot of things about it. It's all like fully determined. You just have to take care of this orbifold structure, and then you have twisted sectors, and you can do all of this. But okay, it's a perfectly known theory. The issue is that we wanted to talk about single trace analogs of the TTbar operator at the supergravity point. And as I explained, this symmetric product orbifold structure doesn't survive out there, so we don't really know how to define them. However, I mean, that is not to say, okay, sorry, something very important that I forgot to say. So it should be obvious to everybody that TTbar has dimension 4, 2 from T and 2 from T-bar, so it's a dimension 4 operator in 2 dimensions. Single trace TTbar the same. When I look at this supergravity these gravity solutions that have these non-normalizable modes, we can look at some of them that have precisely, some single trace non-normalizable operator of dimension precisely 4. So those operators clearly exist at the strongly coupled point. We just don't know how to write them down because we don't have control, a computational control over the CFT over here. Okay, we just know it abstractly. Okay, so that is to say, these are the challenges. However, it turns out that in certain certain examples like this, and maybe let me be a little bit more specific. So basically, I'm looking at D1, D5, or rather, okay, in string theory, you can do what's called an S duality, and then this becomes fundamental string and NS5 braid. It's a little bit better. If you don't know what it is, don't worry. But anyways, we can take this system and we can take this sequential decoupling limit. And in this first decoupling limit, it's the decoupling limit of NS5 braids. Which is supposed to give you some theory, so that's decoupled from gravity, so that's nice. It's supposed to be holographic, but it's not a field theory. The theory is supposed to be a string theory, and it's called little string theory. So it's some horribly strongly coupled theory of strings, but that's, however, decoupled from gravity, so one can try to do holography for it, and whose properties are mainly inferred from the gravitational description because one doesn't really know how to work with it. So this is little string theory, compactified on T4, that's living, at this upper boundary. And the infrared, this flows to just the D1, D5 system. Okay? And just from the gravity picture, so you can say, oh, this theory is given by an irrelevant deformation starting with an operator of dimension 4, but okay, we cannot track it down because we have no control over strong coupling. What are we going to do? What people do, they just try to infer what's happening from gravity. So one thing that they can do is they can look at black holes in this decoupled spacetime. So you have some black holes that fill over here, and compute their thermodynamics. Entropy as a function of energy. Amazingly enough, what they find is precisely this entropy to energy relation. So the black holes in this, okay, I should also say, so the geometry over here is not anti-de Sitter, it's something else, it's actually asymptotically flat, but it has a scalar that's, decaying linearly with a radial distance. It's called the linear dilaton spacetime. Okay, so in this linear dilaton spacetime, you can just compute the thermodynamics, which is given by the black hole thermodynamics, the entropy to energy relation for black holes, and you find precisely on the nose the so-called single trace TTbar formula. It's a small modification of the double trace. Okay, so you can't really study it in the field theory, but gravity tells you it behaves like single trace TTbar. It cannot be exactly single trace TTbar because you don't have this, discrete gauge symmetry over here. Another thing that you can do, and this is what I did with my student, you can compute the asymptotic symmetries of this spacetime, which are supposed to tell you something about the symmetries of the dual tip. And one important thing is that, okay, so the plague in non-ADS holography is the fact that you don't know what the boundary conditions are. So as I try to explain, once you know the sources, which is equivalent to knowing the boundary conditions, you can just use the ADS-CFT dictionary or whatever holographic dictionary to derive what the expectation values are, just differentiating the gravity partition function with respect to the sources. But the problem, the big problem is that you don't know what the sources are once you go beyond the ADS-CFT. So in order to not have to guess boundary conditions, because that can influence the result, we just said that we impose some very light no-flux condition through the boundary of the space-time. Yeah, that's basically it's just saying that we want this theory to be decoupled, so we don't want anything to get out through this boundary over here, which is a very light condition. That condition turned out to almost fix the allowed diffeomorphisms, so the asymptotic symmetries. And when we computed the asymptotic symmetry, so we found two infinite sets of them that turned out to depend precisely on the field-dependent coordinate that comes in TTbar. And then we computed the algebra. We found exactly on the nose the TTbar, the single trace TTbar symmetry algebra. So, conclusion being that this space-time, that's there's no single trace TTbar operator that you can naively define at this point in moduli space that you're deforming. However, it does seem to share some universal features with single trace TTbar, such as the entropy, the asymptotic density of states, discarded to Hagedorn formula, and the asymptotic symmetries, which are these field-dependent Virasoros, which are kind of complicated. It does not share the spectrum. So in single trace TTbar, the spectrum is fully determined. You know, each energy level goes to itself, it depends on itself, and so on. This is not true in this space-time, but that's maybe better. So probably the dual theory is some sort of generalization of single trace TTbar that we don't know currently how to define, but it's sort of interesting to think about spectrum. Okay, so in the last minute or so, I just wanted to take a step further and, okay, so what if I didn't take this decoupling limit over here? What if I looked at asymptotically flat, you know, D1, D5 P black holes? What would be the picture? And I mean, I should say this is pure speculation. I don't know how much pure speculation it is, but anyways. So one nice thing that you can do is to plot for this asymptotically flat, so charged black hole. D1, D5 has some charge. You can plot the relationship between the temperature and the energy. And the plot that you find is something like this. Okay. Okay, so there is a maximum temperature. And then, okay, as I was saying, these decoupling limits are low energy limits. So if your energy is like super low, here you have CFT behavior. This is basically the regime in which ADS3 CFT2 is valid. Here you have this TTbar like behavior that I was, okay, let me be a little bit more precise. So when you take the full decoupling limit, the ADS CFT decoupling limit, you're just seeing this region and it has CFT behavior. The intermediate decoupling that I was talking about here, which is to this little string theory, basically corresponds to taking the energy small on this side and basically scaling this point where T is T max to infinity. Okay, so you're basically not seeing this part of the energy spectrum, and this T max is scaled to infinity, and this T max is roughly like the Hagedorn temperature of this TTbar. Okay. So and I'm taking this from my interpretation of a paper from 2020 by Kutasov, Chakraborty, Giveon, and I think that's it. What they were saying is that maybe you can think also of non-extremal black holes, which have this type of temperature in this region. So the entropy, the energy smaller than the energy corresponding to this Tmax is being governed by the same degrees of freedom that govern the, you know, the Hagedorn behavior in the decoupled theory. But this guy has gone to infinity. So maybe one should think of this piece of the graph as being governed by these little strings and by the thermodynamics and so on. Which is sort of interesting because this type of graph actually appears in pretty much any charged black hole. So Reisner-Nordstrom looks like this, Kerr looks like this. So if you plot the temperature at fixed charge as a function of the energy, you always get this type of plot. So this suggests that, you know, irrelevant deformations such as TTbar may be able to explain black holes that are sort of close to extremality, so this is the extreme limit. In the region close to extremality where they have positive specific heat, so T2e is positive, is growing, maybe TTbar-like theories can explain black holes that are close to extremality, but not super close, just on this piece of the temperature to energy curve, which I think it's sort of an interesting idea, maybe worth exploring. It's not at all clear to me how to explain, you know, the entropy of Schwarzschild black holes, which are basically the guys over here, which have negative specific heat. It's kind of hard to make sense of them thermodynamically, but maybe these TTbar-like ideas can help us understand, you know, general black holes in this regime, which I think it would be nice. It would be progress, let's say, if they actually help us understand. Okay, so with that, I think I'm done with this lecture, and thank you very much for